Check this out. We've got something really fun today. This is so amazing. Oh man, again? Problem. A robot is cutting out circles from sheet metal. The circles have a radius of 5 centimeters and are cut out as shown below from this sheet of metal. The robot starts at the top left corner here where there's a red dot and needs to be centered over each circle where it can then cut out the circle. It can only be programmed to move up, down, and left and right. No diagonal movements possible. We want to provide instructions in exact values for the robot to follow in terms of how far to move left, right, and up and down. And then once it is centered on the circle, we could just tell it to cut and it will run its program to cut. Now the first thing that we need to notice is that this isn't a square. So we see that the width of this is 3 diameters because they're lined up all edge to edge here and the centers are lined up. The height though is not. You see that these circles are tucked in here, so if I actually moved this one out and lined it up like it is up in the row above, you can see that it overlaps. And if I tried to do that with this one, we would go way over. So this thing is much wider than it is tall. So use some skills, pause the video, and see if you can figure out where to tell the robot to move. There's obviously going to be more than one answer because you could go over to the right 5 centimeters and then down 5 centimeters. Or you can go down 5 centimeters and then over to the right 5 centimeters and then cut. Let's say we start off by going down 5 centimeters and then right 5 centimeters. Then we make a cut. Our next one will be right 10 centimeters because we're moving 2 radii or 1 diameter over. Then we make another cut and we do that again, move right 10 centimeters and then we make another cut. The difficulty is transitioning between these rows because I might go back 5 centimeters to the left and then I need to go down, but I don't know exactly how far this is because it's 1 radius, but it's a bit more, but not quite 2 radii. So we need to use the skills that we have to figure out this distance right here. And hopefully you see, once we've got some lines drawn here, you can see that these make a triangle. In fact, not just any triangle, but an equilateral triangle. How do I know it's an equilateral triangle? Well, each one of these radii are 5 centimeters, so this side of our triangle here is 10. This side is the same thing, it's 2 radii or 10, and this side as well. So that gives me a ton of information. I could make a right triangle here with side lengths 5 and a hypotenuse 10. Now I could use the Pythagorean theorem to find this other side. So let's try that out. I've got a squared plus b squared equals c squared. I'll call the side that I know a here 5, and b, it's that unknown value, the height that I'm looking for. I'll call it h for height, and then c is our hypotenuse, which is 10. Now 5 squared is 25 and 10 squared is 100. Subtract 25 on both sides and I get that my height squared is equal to 75. I'm going to take the square root of both sides, and normally if I was going to take the square root of this variable I would get plus or minus. But because I'm only looking for this linear measurement here, I'm only interested in the positive case. So I'll just ignore the negative case here, and I'll just get h. Now I want to simplify this as best I can. So there's a perfect square in here, it's 25. and 25 times 3 is 75. So I can make a note of that here, 25 times 3. Now the square root of 25 is 5, and the square root of 3 is just the square root of 3. I don't want to make any decimals because up here it said that I wanted exact values. And here's the height that we need to move, 5 times root 3 centimeters exactly. And that will give me that distance I need to move. Now there's one more thing we could do. Since we know this is an equilateral triangle, that actually gives us these angles. So this would be 60 degrees. This would be 60 degrees. This would be 60 degrees. Or when I made a right triangle out of this, this would be 30 degrees. Now once I have the angles here, I can actually use my trigonometric ratios to find this height. So let's try that just for fun. Let's say we're going to use, how about sine? So sine 60 is equal to the opposite side, which is our unknown height here, divided by the hypotenuse, which is 10. And now we just need to know what sine 60 is. And hopefully you remember from 20-1 where we did special triangles. Sine 60 is root 3 over 2. And I just solve for h by multiplying by 10 on both sides. So this will be 10 divided by 2 gives me 5, and the root 3 stays there. And you see that we got the same answer as we did before. Now with that information, that's pretty much the only trick to this question. The rest is easy. We go left 10 centimeters, and then we use the same down movement here, the 5 root 3 to get down, and then over, and we can get the rest of these without a problem. So here is a potential answer. If you did it in a slightly different order, that should be okay. Here's another thing that we need to review for this course. Making a table of values for functions and also plotting them on a graph. So say we have a quadratic that looks like this, and we want to make a table of values. Probably the best and quickest way to do it is to put this into your calculator and then look at the table of values your calculator makes for you. But say you wanted to do this by hand, maybe there was only one value you're interested in, so let's just try one of them to see how that would work. We would replace the x with -3. So everywhere where there's an x in this equation, there's only one here. But if there was 2, we'd replace them both with the -3. Make sure to use brackets because it will contain the whole thing that we're replacing. Now, -3 squared is 9, and times by 0.5 is 4.5 minus 4 just leaves me with 0.5. So give that a try. Make this table of values, plot it on the graph, pause the video and restart it once you're done to check your answer. Here's the table of value that I got. And here are the points plotted. -3, 0.5, negative. There we go. Looks like about there. And since this graph is continuous, it means that not just these values are possible, but every value in between here is also possible. I don't want to draw infinitely many dots here. That would take me infinitely much time. I'd be here forever. I'm just going to draw a straight line through them all to connect them to show that all the values in between here are possible. Chapter 1 is transformations. Now, a transformation is a change made to a figure or graph that changes its position or shape. Now I'm going to teach you how to transform things, and thus you will become, in effect, transformers. So are you ready to become transformers? Section 1.1, Horizontal and Vertical Translations. A translation is where an object or a graph is just moved up, down, right, or left without changing its size or shape. This is similar to the robot cutting out the metal circles in the first problem. It can only move up, down, right, or left. At least that's all that we're going to deal with in this course. This is also called a slide because it just looks like the object slid over somewhere to another location. Careful with this word. Lots of students get mixed up with translation with the all-encompassing transformation. So a transformation is stretches, reflections, and translations. And translation is like a slide. Maybe that's also why some people prefer to call it a slide, because it's less like transformation. What happens if we add a constant outside the original function? So for example here, our original function is just our most basic quadratic, y equals x squared. And so our f of x here is x squared. What happens if we add something outside? That means like we didn't do anything to the function itself, but after this function is done doing its thing, then we're going to add something. Now we're going to use k in 30-1. Other courses you run into might use the letter d to denote this constant. D is used in some university and IB courses. Just experiment. Try a few positive and a few negative values for k and observe what happens to the function. You're looking for a pattern here. What does that do? Now hopefully you remember this from 20-1, so it should be a review, but just give it a try and see what happens. For example, let's say my k value was going to be just a nice 1. That means that my equation here would be y equals x squared plus 1. And it would look like this, and I'm just going to cheat a bit because I'm using this software, and plus 1 would actually make it look like that. I'll just finish that with an arrow here. So that would be this graph here, y equals x squared plus 1. Try minus 1, you'll see it moves down, minus 2, and so on. If k is positive, then the original graph is moved up. If k is negative, then the original graph is moved down. Now hopefully you remember that from 20-1, that k value is what we called our q, and that was the y value of the coordinate of the vertex. What is the equation of this function shown in the graph below? So you can think of our 20-1 knowledge, or you can just think of just what we did. Here's our original here, and somebody moved it down 3 units, and not side to side, just down. And so this would be y equals x squared minus 3. What happens to this function if the k value is changed to 4? So this is y equals the absolute value of x. And if we changed it to y equals the absolute value of x plus 4, it would then look like that. It would just move up 4 units. What happens if we subtract a constant inside the original function? So we're going to use h to denote this, and now we're inside. See, our function is x squared, and we're going to put a constant in here inside the squared. In function notation, it would look like this. Notice function notation, you can't see what the function is, but you can see the transformation here. We use H for 30-1, and IB and other courses may use C. So here's the original. Try a few positive and a few negative values for H and observe what happens. We want to recognize the pattern here. And notice that we are always subtracting the value of H. Let's give one a try. Let's say we thought of H is 5. That means that our new equation that we would want to graph would be y equals x minus 5 squared. See, the H value is here, and it doesn't include the negative that's in front. That's not part of the H. All right, so our H is just what we see here, the 5, and the minus is separate. This would look like a parabola still, but moved over 1, 2, 3, 4, 5 units. So it would have its vertex at 5, 0, right here. Let's do another one just to make sure we know what's going on with this negative. What if my equation was y equals x plus 2? What is my H value? Well, because this is plus, but it was always meant to be minus, we need to do this. We could do this mentally, or we could write it down, but we need to make that minus again. Now, if I want that minus, but it's plus, it means that there could have been 2 subtraction signs here, or 2 negatives in a row, and they would have multiplied by each other here and canceled out and just made this positive. So just if you see a positive here, our H value is going to be negative because we need this to be negative. That's the way our formula is set up. More on that in a minute. So try some more values of H. See if you can get the pattern here. What happens when we're changing this value of H? So hopefully you saw that if our H value was positive, then the original graph is moved to the right. And if H is negative, then the original graph is moved to the left. Now also in 20-1, this H value is what we previously had called the P value, and it represented the x value of the coordinate of the vertex. And you remember that there was a minus p in our vertex form of our quadratic equation. Example 3, what is the equation of the function for the graph shown in blue? So if the graph shown in black here is y equals the absolute value of x, then the graph here in blue just moved over to the left 3 units. So we're working inside the function, and it would be y equals the absolute value of x plus 3. Now some people might have written minus -3, but clean it up, and if it's minus a negative, just clean that up to be plus. Now, one of the most important questions, or one of the most thought-provoking questions, why do we subtract the value of H? And that's actually quite a complicated question. It will require a lot of thought. Nobody's going to ask you about it, so as long as you can remember that that is the case, that things work backwards inside here, then you'll be okay. But let's consider this for a moment with this example here. Before, when I put in 0, x equals 0, then I would get the absolute value of 0. Now I try to put in 0 again, but I'm adding 3 to it, so I'm changing before the function does its thing, before the absolute value brackets has a chance to do anything, I'm changing the input. So I put in, say, x is 0, and I'm adding 3 to it, so really this argument becomes 3. So I'm taking the absolute value of 3, and that's why for x equals 0, I get 3. So to get the vertex, before I could just put in 0 and I'd get the vertex. Now I have to accommodate this change I'm making in here. And actually you have to do that by doing whatever is opposite of this sign. So I would need to put in -3 for x, to cancel out the positive 3 to give myself an argument here of 0 going into the absolute value. So that's why everything works backwards. We're trying to cancel out this change that we've made inside the function. Now here's a big long written explanation of that, and you can read it over in your own time, but that's essentially what I was trying to say. Mapping notation. Mapping notation is a set of instructions that show how each individual point is transformed, or it's a map of where the old point went. So we say the old point here, we write it as coordinates with our parentheses around it, okay, our x, y coordinate, and then we do a single arrow, and then we show where it went. So x would be affected by h, and y will be affected by k, because remember the h value moves it left or right, and that would be our x values, and the k value moves it up and down, and that would be our y values. The function y equals the absolute value of x is transformed from this one shown here in black to this function here shown in green. What is the equation of the transformed function? So look for distinctive characteristics that you can track. Looks like the vertex here moved right 2 units. So we know that our h value is going to be 2. Then from there it moved down 5 units. So our k value is going to be -5, the negative because it went down. Now let's make that into an equation. So we would have y is equal to the absolute value of x. Now h goes inside here and it goes with a negative sign, so x minus 2. And then the k value goes outside the absolute value function. It will sit back here and it will just be a plus -5, or I could just write -5. What is the general mapping notation? Let's look at these 3 points and see where they went, and then we'll be able to write the general mapping notation. So -2, 2. That'll be this point right here. Where did that point go? Well, it's over to and up to from the vertex. So I'll look down here, over to and up to from the vertex. It's here. All right, so that point is now 0, -3. Let's do that again with the vertex itself. The vertex was at 0, 0, and now it's at 2, -5. And the last point here we're going to look at, so I'll make a triangle here maybe. Triangle here. Last point here is 2, 2. I'll make a square for that one. And that one went to here, you can see. So it's now at 4, -3. And our general mapping notation is where we have, instead of specific coordinates put in, we have x and y, like that, and we want to give a map of where every single point goes. If you look at each one of these, you can see that we added 2 to the x value, and that makes sense because our h is 2, and we subtracted 5 from the y value. So in general, our mapping notation for every point would be like this. Add 2 to the x, subtract 5 from the y, and you'll get the new graph here. Now these are image points. So these 2 here, this is an image point of this one. And they're not necessarily where the graph intersects, but they are the equivalent point after the transformations have happened. If we called this point A, then we would denote its image point with an A prime. And say this was point C, then this would be C prime. And if we called this point Optimus, then this point would be Optimus prime. f of x is transformed into g of x. What is the mapping notation for that transformation? Let's take a few of the points and see where they went. So -3, 5. That'd be that point right there. Where did it go? Looks like it went over here to -6, 1. How about this point? -1, 1. That would be that point there. Looks like it turned into this point, -4, -3. 2, 3. That would be this point. Turned into -1, -1. And 3, 2. This point here moved over here, so it's now 0, -2. Now look at these, look at the pattern. Looks like all of our x values went down by 3, so we need to subtract 3. And same with our y values, they also went down by 4, so we'll have to subtract 4. So our mapping notation would look like that, where every x value was subtracted by 3 and every y subtracted by 4. Let's try this on another point that we haven't done yet. Maybe this point here, -2, 3. So -2, 3. And our mapping notation says we should subtract 3 from the x. So this will become -5. And we should take every y value and subtract 4. So 3 minus 4 is -1. Let's go see if it worked. We're looking for the point right in the middle of this long piece. Should be at -5, -1. And there it is. So we see that our mapping notation works. There are two ways to show the transformations on functions. In the blue here, I've written you can use the function itself. So for example, if our function was y equals the absolute value of x, we could show transformations using the absolute value, and we could say, hey, we moved left 3 units and down 2 units. We could also use function notation. So f of x here is the absolute value of x, and we can show the transformations on f of x. Now in this case, we won't see the original function. We can't see that it was an absolute value function, but we can see that the transformations were move left 3 units and down 2 units. Don't get these mixed up. So often I'll see students adding an f here. Now this makes no sense. You're mixing function notation with the actual function itself. So make sure you keep them separate. If you're going to use the function, there's no f. And if you're going to use the function notation, you don't need to show what the original function was. You'll see questions written both ways, so you need to know both of these very well. This was part of Relations and Functions 2, demonstrate an understanding of the effects of horizontal, vertical translations on the graphs of functions and their related equations. Here are some questions from the textbook. Give them a try and see if you know what you're doing.